Welcome. Today we're going to be taking a look at the notes worksheet entitled Inverse Trigonometric Functions Day 1. And so what we have just finished is exploring the 6 trigonometric functions: y equals sine of x, y equals cosine of x, y equals tangent of x, y equals cosecant of x, y equals secant of x, and y equals cotangent of x. And we looked at a lot of application and all the characteristics and so forth. And so what we're going to do today is kind of shift gears a little bit, and we're going to take a look at the 3 primary functions and see what would work with their inverses. So we're going to look at the y equals inverse sine of x, y equals inverse cosine of x, and y equals inverse tangent of x. And so it's going to take a little time to develop here. There's some things conceptually that we're going to have to work through. So please take good notes with this, and always pause the video at any time, rewind the video at any time if something doesn't click, and of course ask questions as you go through the process as well. So I'm going to do 2 today. I'm going to try to break out the inverse sine function and the inverse cosine function, and then on the day 2 notes worksheet we'll take a look at the inverse tangent function and just do some work with that. So anyway, here's what I have. Investigation number 1, the inverse sine function. And let's see what you remember from first semester here. Let's see what works for you. So it says, sketch a graph of y equals sine of x from negative 2 pi to 2 pi. All right, let's do exactly that piece. So one step at a time with this, guys. Be with me on each step. So give me a z-trig window if you get an opportunity, which would be from negative 2 pi to 2 pi here. Something like that. And then up to 1 and down to negative 1, I suppose. And remember, sine is the function that starts at the midline. So midline to midline there, kind of up and back on down. Something like that would do. And if you get an opportunity, let's go ahead and bring that back as well as we work into the negatives. Okay, not perfect, but doesn't need to be. All right, now let's see what your memory is like here. There's a question on the page which I do need to ask you. Is the function 1-to-1? Of course, everybody, it is a function. It passes the vertical line test. Is it 1-to-1? So we explored this idea first semester, and the concept of a 1-to-1 function related to the idea of an inverse. And I guess to just get this moving along here for you, the idea behind a 1-to-1 function is that it must pass a certain test. A vertical line test, of course, is to determine if a graph represents a function. And everybody, the horizontal line test is used to go ahead and determine if it is 1-to-1. So in this case, everybody, as you can see, by no means does this pass the horizontal line test. So absolutely not. And so as is, everybody, does y equals sine of x have an inverse that is a function? Well, here's the idea, and if you remember from first semester, these 2 answers go hand in hand. If the function is not 1-to-1, then its inverse is not a function independently. So at this stage, we would have to say that y equals sine of x does not have an inverse that is a function independently. So put a no right there. Okay, hopefully everyone's okay with that. Did not pass the horizontal line test at this point in time. So let's go to part B. It says, in order to ensure that y equals sine of x is 1-to-1, the domain is restricted to a particular interval. Now, kind of gave it away there on your paper, but that's all right. Let me go back to the first screen, and I guess what we're going to do is restrict the graph so it actually does pass the horizontal line test. So think about in interval there, even though it's written, see if you can kind of figure it out yourself. See if you can find an interval on this particular screen where if I just drew that part of the graph, it would pass the horizontal line test. Now there are multiple intervals. There's just one that has been agreed upon, and so that's the interval that we're going to use here. And very simply, it's from negative pi over 2, which the graph starts down here, all the way up to pi over 2, which ends right up here. So if you look at it from here to here, everybody, if I just drew you that graph on the coordinate plane, would that pass the horizontal line test? Absolutely. And notice, this interval covers all of the sine values from -1 all the way up to +1, so it includes all of them, on that interval right there. And that's what we're going to do. So let's go back right here, if we can, to my screen, part B. And it says, sketch y equals sine of x from negative pi over 2 to pi over 2. Okay, so everyone, if you would, another coordinate plane. You'll be doing this a lot here. And in this case, let's go ahead and illustrate it. So here's negative pi over 2. There was pi over 2 over there. Down at negative 1, up at positive 1, looking fine. And again, we have our minimum down here at negative pi over 2. Midline right at 0, 0. And peaking, of course, when x is pi over 2, and I get a sine ratio of positive 1. And if I graph this in all its glory there, should look something like this right here. There's one part of the sinusoidal wave. So everyone take a look at that piece. What I've done now is restricted the y equals sine of x graph to a particular domain interval. Only this part of it from negative pi over 2 to pi over 2. And guys, of course, this is why these notes worksheets are great. Is it now 1-to-1? Absolutely, of course. Put a big yes in there if you would. And so now that we've restricted the sine function to just this particular interval, will the inverse of this function up here be a function independently, or will the inverse be a function independently? Sure. And that's what we're going to look at. Okay, let's go to my next screen. And obviously, I think we should probably review a couple ideas between a function and its inverse. And then we'll check out the graph for the first time and talk about some of the characteristics and so forth. Okay, so part C on your paper, everybody. It says, what is the algebraic and also the graphical relationship between a function and its inverse? So what's the algebraic relationship, everybody? If you remember correctly, to create an inverse, very simply, the roles of x and y change. And we're going to talk a lot about that over the next couple days. But very simply, all of the x's and y's, this is how I'm going to write it, x's and y's interchange. The x's become the y's become the x's. All right, perfect. That's the algebraic relationship by definition. Graphically, if you remember correctly, they're reflected over the line y equals x. And again, this is all just from first semester there. Certainly, it just reflected over the line y equals x. So what we're going to do is, to the best of our abilities, is sketch the y equals sine of x within the restricted domain, then sketch the inverse of that, which we will define as this piece right here, y equals inverse sine of x. So a function unto itself, defined as the inverse of the restricted function of y equals sine of x, on the same coordinate plane. And we'll also include the reflection line right there, y equals x as well. All right, well, I'm going to help you through the process here a little bit. As much room as I gave you here, please use it. And so something like that is what I'm drawing on the board. And I'll ask you to do this. So since you haven't seen this before, it might be a little bit of an issue to get some of the scale right. But here's what I'll ask. Let's call that positive 1. So I'm going to go positive 1 there, and then negative 1 here. And everybody, if you get an opportunity, let's do negative 1 right there. Try to have them evenly spaced, if possible, from the origin. The other number that I'm going to include here, everybody, is going to be that pi over 2. Now remember, everyone, pi over 2 is about 1.57, give or take, somewhere in there. So if this is 1, then pi over 2 is probably about there, just a little further than the positive 1. Same thing here, everybody. I'm just trying to keep it as nice as possible. So if that's 1, that's probably about pi over 2, give or take. And here would be negative pi over 2. Try to get that down all the way at the bottom. And then here basically would be negative pi over 2 as well, all the way to the left. Okay, so what we're going to do, everybody, well, let's do the one we know. Let's do the one we did just above. Y equals sine of x restricted. Then, everybody, what we'll try to do is switch the ordered pairs around and see if we get an opportunity to draw the inverse. Okay, well, let's try this out. What we saw above, everybody, is at negative pi over 2. At negative pi over 2, the sine ratio is negative 1. So everyone, if you would, put a point right there. Of course, sine of 0 is 0. Put that right in there. And then sine of pi over 2 is 1. So that is the interval that I am restricting the sine function on from negative pi over 2 to pi over 2. And notice it covers the infinite number of sine ratios possible, all the way from negative 1, working on over up, to positive 1 at the peak right there. Now, everybody, if you do get an opportunity on your paper, can you please label that? We're going to go a capital S here to illustrate that this is what's called the restricted sine function. So capital S, and so what that means is we kind of stop it at pi over 2, and we started it at negative pi over 2. Remember, the sine function theoretically goes on forever and ever and ever. That would be lowercase. This is just to illustrate that it's slightly different. It's the restricted version. Okay. Well, guys, of course, how do we create the inverse? I very simply switch the ordered pairs. So I only had 3, and, theoretically that's all I will need here, and I'll give you a good sense of what this graph will look like. But everyone, if you look, this point right here is negative pi over 2, negative 1. Well, of course, how do I find that corresponding point on the graph of the inverse? I switch it. So instead of negative pi over 2 and negative 1, it's negative 1 and negative pi over 2. That point goes right here. Put a point in if you would. Now, guys, switch 0, 0, which, of course, is still 0, 0. And then, let's get that other point. This one up here, everyone, was pi over 2 and 1. So instead of pi over 2 and 1, we know how an inverse works, everyone. Switch it. It's 1 and pi over 2. And so that would be up here. Now, to get this to work, again, continuously, to include all of the angles and all of the sine ratios in, I'll kind of show you what it looks like and the nature of the graph. And to keep that reflection over y equals x, it should look something like this. Kind of comes that way, and then up here. And so when you do get an opportunity, sketch that out to the best of your ability there, and let's label that as y equals the inverse sine of x. Now, if you do get a chance, you don't have to do this if you don't want to, but even if you do, do it very lightly. Let's just go ahead and put a little y equals x in there. And I didn't draw mine perfectly, but it's not bad, all things considered. Do we see that all of the points on the graph of the original function are reflected over the line to get the points on the graph of the inverse? Certainly. And that's what we saw first semester, and that's exactly what we're seeing here. Okay, let's bring up the calculator for just a sec. Give us a chance to take a little breather for just a moment. And let's go ahead and type it in. So it won't be perfect here because I'm not going to tweak the window. But everyone, go ahead and go to your y equals in radian mode. Just type in inverse sine of x. And just keep an eye on what we drew. And this is probably the one time and the one time only I can say that what we drew is probably a little better than what you're going to see here. But I'm going to zoom trig this, and you can get a sense of it. It's not perfect by any means, but here's the idea, kind of coming up and then through. And then here's that point, everybody. Here's 1 comma pi over 2 right there. So not ideal by any means on the graphing calculator, but at least you get the idea. Again, I like what we drew better, to be honest. All right, everyone. So here is the key. Let's highlight these two pieces right here, everybody. These are the ones that are going to really help us conceptually as we go through the process. So now, everyone, it says, what is the domain in range of y equals sine of x, restricted, of course. So we all know that the domain of your sine function is all real numbers. But that's not the case here because I wanted to make it 1-to-1, so I restricted the domain interval. So it's not all real numbers. Right now, everybody, as you can see, it's in between negative pi over 2 and pi over 2. That is the domain. Those are the angles in radians, or really just real numbers, but those are the angles in radians that I'm going to allow to be my inputs of this particular function. Anywhere from negative pi over 2 to pi over 2. And you can see it up here. I'm going to try to mirror it. Here's negative pi over 2, everybody. And as I track my graph horizontally, all the way to pi over 2. Okay, good. Now what's the range? Well, of course, guys, we know the range represents the outputs or the possible sine ratios. What do we know about sine ratios? Well, we know they can only be from negative 1 to positive 1. There are an infinite amount of sine ratios, but they are all in between negative 1 and positive 1. And if I check my graph vertically, here we go, down at bottom at negative 1, and I'm going up, and by the time I hit over here, I'm up at positive 1. So the range, everybody, is from negative 1 to positive 1. And I was able to include the infinite number of sine ratios. Oh, pen is acting up just a little bit here. There we go. On this angle interval right here. Okay. Now, here's what I would ask you. If that is the domain and range of our restricted sine function, what is the domain and range of the inverse? What happens to those two quantities? Well, we've looked at this before, of course, and now it should play out nicely. We should know that they interchange. So, very simply, if I want the domain of my inverse, it is going to be equal to the range of the original function. So in this case, everybody, the roles switch. When I talk about the inverse, the inputs are the ratios. The outputs, everybody, and this is going to be the key. So if you don't mind, put a little asterisk next to this one. This is the key. My answers, my outputs, will always be in between negative pi over 2 and pi over 2. So when you type an inverse sine of any number in the calculator, if it's possible, it will only give you an answer in between negative pi over 2 and pi over 2. That's the key. Remember a function, everybody, and this is a key thing conceptually. Each input can produce one output, and we'll talk about this piece on the back side. So that's what a function is, and that's why we're taking the time to define the inverse as a function. So each input can produce a sole output. Okay, good. It's a good start. Obviously, it's going to take a lot of time to absorb and some practice there, but it's a good first step. I'm going to go to my next page, and let's go ahead and just try this out a little bit, get a sense of what's going on, and if you know your unit circle, you'll have a really good shot at this. Here's what I'm going to ask you to do. Somewhere, I know I didn't leave you a ton of room, but just draw a circle for me, because I think that's our best representation. I'm going to try to give you a couple hints, ideas, suggestions, shortcuts, whatever you want to call them, to be successful with this. So everyone, if you would, give me, how about this, a line going up there and a line going down there. And if you remember, well, actually, hold off just a sec. I think I'll wait on that piece for just a moment. So here's how we're going to do this, everybody. We're going to do the inverse sine of 1/2, inverse sine of root 3 over 2. And these are all ratios that we know. These are all sine ratios, basically. And here's the concept behind this before we go back to my little diagram here. What we're looking for is the angle that produces a sine ratio of 1/2. Okay, an angle that produces a sine ratio of 1/2. That's our answer right here. The problem has been that, of course, there are an infinite number of angles that have a sine ratio of 1/2. I get a sine ratio of 1/2 on my unit circle about right here. I also get one in the second quadrant over here, and there would be an infinite number of ways to go from my initial side to my terminal side that would make a sine ratio of positive 1/2. So theoretically, and here again is the dilemma, there are an infinite number of angles that have a sine ratio of 1/2. But as we all know, that's not how functions work. One thing goes in, one thing comes out. So when I ask for the inverse sine ratio of, or inverse sine of 1/2, I want the angle that has the sine ratio of 1/2 in our interval. And that's why we know our interval has to be from negative pi over 2 to pi over 2. That's why we restricted it. So guys, here's how you're going to do it on your paper here, I think. You're going to start at 0, and you're just going to do a clockwise rotation to negative pi over 2, and a counterclockwise rotation to pi over 2. Something like that. That's how inverse sine has been defined in order to get one output, one answer. Okay, now let's fill in some terminal sides here, everybody. In the first quadrant, just in terms of our special values, we had 3 terminal sides in the first. We also had 3 terminal sides down here. So that's what I want you to focus in on. I think that's a good diagram to help us here. Let's give it a try. Let's see what we can do here. So you're going to start here, and you're going to use this diagram to be of assistance. So what I'm looking for, everybody, is the inverse sine of 1/2. Well, I'm going to start here, everybody, and if I start here, I need to figure out where I'm going to get a sine ratio of positive 1/2. Well, I think we all know that sine is positive up in the first quadrant. That's good. And it's negative down here in the fourth quadrant. So this obviously is not what we want. So what we're going to do from here is we're going to rotate counterclockwise, and we're going to figure out where we would get a sine ratio of 1/2. Because it's one of our special numbers, would it be here, here, or here? And if you remember correctly, it would be this first one. And so the question, of course, is what is the angle that produces that sine ratio of 1/2? From here to here, everybody, it's pi/6. And that's your answer. If you were to type in the inverse sine of 1/2 on the calculator, and we might actually do that, it's going to give you pi/6. Even though, theoretically, again, in order to get to this sine ratio here, could I have gone around again? That would have been an angle with a sine ratio of 1/2. Could I have gone around again? Sure. Could I have gone around clockwise? Could I have gone over to the second quadrant where this sine ratio would have been 1/2? Sure. Again, sorry for being redundant. I'm just hoping it pays off here. There are an infinite number of angles that have a sine ratio of 1/2. But when we treat it as a function is all based on one input producing one output. So we have to get the one that it's defined for. And it's defined in between negative pi/2 and pi/2. Okay, again, a lot to absorb here. Keep working at it, though. You'll be successful with it, I promise. Let's type it in. Here we go. Inverse sine 1/2. That number that the calculator gives you is exactly pi divided by 6. Let me just prove that to you. There is pi divided by 6, and notice that's the number. Perfect. Now let's go ahead and roll with the rest of these. Letter B, inverse sine of √3/2. That's one of our special sine ratios. So guys, you're going to start here at the initial point. To get a positive sine ratio, do I go up to the first quadrant or down in the fourth quadrant? I go up in the first quadrant. And where would I get a sine ratio of √3/2? Right here, everybody. What's the angle, or what is the number from here to here? Pi/3. And that's it. That's what it would give you. If you know where you are on your unit circle, I've been saying this now for weeks, you really have a good shot at these. You just one added layer to it. How about letter C? Inverse sine of 0. Well, guys, where do I get a sine ratio of 0? On the unit circle, a y-coordinate of 0. Hey, right here. And of course, everybody, have I moved? Nope. So the angle is 0. And by the way, just trying to make connections for you here, of course. Remember one of the points on the inverse sine function? There it is, everybody. There is 0, 0. So when the sine ratio is 0, the angle that produces it is also 0. Oh, let's come over here and get to my next screen. Good. All right, let's keep going. Letter D, inverse sine of negative √3/2. All right, so the first negative sine ratio. From here, what's the easiest way to get to my negative sine ratios? I'm going to go clockwise. So that would be a negative angle measure or a negative real number. And where would I get a sine ratio of negative √3/2? Nope. Nope. Here it is. And what would that be from here to here, everybody? That would be pi/3 clockwise, so negative pi/3. I'll type one of these in just a sec just to verify. Maybe I'll do the last one there. How about inverse sine of √2/2? Positive sine ratio, everybody. We're going up in the first quadrant. So which one is the √2/2? First, second, or third? It's the second one. So that's where I get a √2/2 sine ratio. And how far is it from here to here on the unit circle? Or what is the angle in radians? Pi/4. Last one, inverse sine of negative √2/2. Hey, everyone, let's bring that down and going clockwise here. That's where I would get the sine ratio of negative √2/2 coming down this way. Again, sorry for the redundancy, but even though there are an infinite number of angles that have this sine ratio right here, for us to define it as a function, we can only get one answer, one angle. So out of the infinite number of angles there, you have to find the right one. And the right one is in between negative pi/2 and pi/2. And that's this number. Hey, let's do one of those on the calculator at least. I'll do the inverse sine of that negative √2/2. So inverse sine negative square root 2 divide by 2 Yep, typed in something wrong there. Let me see what happened. Oh, that's weird. Let's go on back. I accidentally did a minus there. That's not like me. There we go. And in this case, this number, everyone, is negative pi over 4. That's it. Okay. Well, one inverse down. Took a while. Let's do one more. So inverse cosine function. It says repeat the previous investigation with cosine. And it says to restrict. Now, just one thing to note, of course, I'm going to bring this up here before I even read it. Watch this. When I type in y equals cosine of x, does that pass the horizontal line test, everybody? Absolutely not. No way. So as defined right here, will the inverse be a function independently? No. So what I need to do here is restrict the domain interval so it will pass the horizontal line test. So it will be 1-to-1. If it's 1-to-1, then the inverse is a function. Now notice here, everybody, negative pi over 2 to pi over 2 doesn't work. Because in the fourth quadrant and first quadrant for cosine, as we all know, in the fourth quadrant, cosine's positive. In the first quadrant, cosine's positive. So that's not going to work, everybody. That doesn't pass the horizontal line test. Negative pi over 2 to pi over 2 is not a go. So which interval are we going to use in order to help it pass the horizontal line test? How about this one, guys? From 0 to pi. And there it is. I include all the cosine ratios there. Let me put this back on. From positive 1 to negative 1 there as I traverse from 0 to pi on the coordinate plane. And so that's what it says. So it says restrict the domain interval of cosine to 0 to pi. Include a sketch and so forth. Now this one's going to be a little harder to draw. So bear with me on it. I'll do the best I can. You do the best you can, and we'll go from there. So it should look something like this, give or take. I'm going to kind of go like this. Just trying to get my picture to do this justice here. And I'm going to put a -1 right there, everybody, and then just circle around. So I'm going to do my 1s first. And I might not be able to pull this off down here. We'll see. Yeah, it's not too bad. Okay, so -1 there. Try to do that if you can. Again, trying to get my window to do this justice. And guys, how about a pi over 2 here? And then how about a pi up here, just to kind of put it in perspective. If that's 1, that's about pi. And then over here, if that's 1, you know, that's about pi, give or take. Doesn't have to be perfect. We'll see what we can do with it. Okay. And then one other thing I wanted in here, guys, throw a little pi over 2 in. I'll give you a moment, of course, to pull that off. It's going to be probably as good as it gets. Okay, so what we're going to do here, everybody, is draw in really the basic cosine function, restricted. And then, everybody, what we're going to do is try to graph the inverse on this. Let's give it a try. So what do we know about the cosine function? Well, the cosine of 0 is 1. It starts at the max up there. So hang on one sec. There we go. I got that. Then at pi over 2, everybody, cosine of pi over 2 is 0. And then the cosine of pi is -1. So we're going to go from max to min on my restricted interval here. Should look something like that. All right, so everybody, if you get an opportunity, give me y equals capital C, so cosine of x. So the restricted cosine function. It definitely does pass the horizontal line test, and it's looking beautiful. How do I create the inverse of this restricted cosine function? Well, of course, I just switch all of the x's and y's. And so that's exactly what we're going to do right here, and we'll see how it plays out. So let's go with the points that we know. So everyone, in this case, here's what I'm seeing. Instead of 0, 1, I guess it's going to be 1, 0. So the inverse cosine of 1 is going to be 0. Okay. Now how about this one, everybody? Looking at this, cosine of pi over 2 is 0. So as a result, instead of pi over 2, 0, it's going to be 0 pi over 2. There it is up there, everyone. And one more point I see, here we go, out at pi. Cosine of pi, as we all know, is -1, of course. And so instead of pi -1, It's going to be -1 and pi. So you can kind of see why I did my window, even though it's not ideal. Should work nicely. And guys, if you were to sketch it out and sort of include all of the other ones in there and do this continuously, should look something like that. So this was the restricted cosine function. This, everybody, is its inverse. Okay, throw that in. Does it look like we have a nice reflection over y equals x here? And you can do this or not do this. It's your call. But something like that. Does it look like it has a reflection piece? Absolutely. Even as poorly as I drew it, it looks good. If you don't mind, I'm just going to take a moment here and graph it on the calculator for you just so you can see. And then we'll go ahead and fill in some stuff here. Inverse cosine of x. And again, ours is actually better there. In fact, it should kind of hit there. I think it's just more of a pixel issue than anything, but it should come up like that. Okay. Again, I like our drawing better. All right, everyone, let's see. We need domains and ranges if we're going to pull this off. So as a matter of fact, kind of tie these together if you would. And I'm afraid you're going to need to know these really super well. Okay, so let's talk restricted interval. Now we do know, of course, the domain of the basic cosine function is all real numbers, but we restricted it from 0 to pi. So it's not all real numbers. We're only focusing on the angle measures in radians from 0 to pi. And the nice thing about just restricting it there is I still have included the infinite number of cosine ratios out there, because I know cosine can only go from -1 to +1. And that is what I see. When I drew this right here, I went from the max at +1, there we are, down to the min at -1. All of the cosine ratios are covered on this angle interval right here. So how, of course, do I get the domain and range of the inverse? I switch them. The ratios become the input. And we know cosine ratios can only go from -1 to +1. The angles become the outputs. And even though there are an infinite number of angles that have these cosine ratios, there can only be one answer. And the answers are in between for cosine, 0 and pi. All right, that's the key. So sine, you're going to have to really think about -pi/2 to pi/2. Cosine, everybody, you're going to really have to think about 0 to pi. I'm missing one thing, aren't I? Oh, I missed the example 2 there. That's not good. So, okay, sorry about that. I did not include example 2 originally on my smartboard here, so I had to go over to the computer and just remedy that, of course. So now I have your example 2 in, and as you can see, this problem set is exactly like the one above for sine. We're going to have to obviously treat it differently. So everyone, if you would, just for a visual aid, and been all about the visual aids this unit, let's go ahead and get our circle going here, and sort of the initial side, and let's go like this, as a matter of fact, for cosine. And so here's the premise for cosine, of course. Our angle intervals are from 0 to pi. So I'm going to draw this out first and then describe what's going on here. But this would be the situation at hand. We're just going to go counterclockwise from 0 all the way to pi. So everyone put a little 0 right here and put a little pi right here. That might be a good visual aid for cosine. Let's see, this one doesn't want to go. There we go. Okay, so just like I did above for sine, that was from -pi/2 to pi/2. This one, everybody, is for cosine. And our angle measures run from 0 to pi. Our answers, our range values, run from 0 to pi. And so that's how we're going to play it out here, everyone. So here's, I guess, what I would ask us to do. Let's start this off, of course. Inverse cosine of √2/2. Now, sorry for the redundancy, but here's the issue. There are an infinite number of angles that have a cosine ratio of √2/2. But when I'm treating this as a function, input produces a single output. So I can't put an infinite number of answers over here. What I want is a single answer. And the single answer is the angle in between 0 and pi that has this cosine ratio. That's why this diagram is so important. So from 0 to pi, somewhere from here to here, everybody, there is an angle measure in radians that has a cosine ratio of root 2 over 2. And so what do we know about cosine, everybody? As I rotate this way, cosine's positive in the first quadrant and negative in the second quadrant. So positive cosine ratio of root 2 over 2 should be right there. And this should be pi over 4. So you're going to really have to change your mindset going from sine to cosine. Sine, the interval is different. Cosine is from 0 to pi. Okay, so everybody, here's the deal. Cosine, or inverse cosine of negative root 3 over 2. So same premise, I have to get the single angle in this interval that has that cosine ratio. So I go round. Cosine is negative in the second quadrant. Where am I getting a ratio of negative root 3 over 2? Not here, not here, here. What is that angle as I go in radians from here to here? And it should be 5 pi over 6. Now notice, and I've seen students do this before, they'll say they're just so, they get the sine interval in their mind, and then they're thinking, oh, I'm just supposed to rotate down here. But guys, what do we know about the cosine ratios down here? I'm not getting negatives. Cosine is positive down here. So this wouldn't make any sense to travel this way. We want to travel counterclockwise to get to that spot right there. And so 5 pi over 6. Okay, next one, inverse cosine of 1. So where from here to here am I going to get a cosine ratio of 1? Remember on the unit circle, the cosine ratio was the x-coordinate of 1, and that was actually right here. There we go. There's a cosine ratio of 1. And so as a result, what's the angle measure right here? Well, I have not moved, and so it's 0. And by the way, again, just trying to connect a few things. What did we say about this one? The inverse cosine of 1 is 0. When the input is 1, the output is 0. Okay, next one. Inverse cosine of 1/2. And so here we go, inverse cosine of 1/2. Let's travel around. Where am I getting a cosine ratio of 1/2? Not here, that's root 3 over 2. Not here, that's root 2 over 2. There it is. That's my cosine ratio of 1/2. And so as a result, what's that angle? Pi over 3. Last one here, inverse cosine of 0. Let's see it, everybody. Where do I get a cosine ratio of 0? Oh yeah, right here. That's where the x-coordinate is 0 as I travel around. And what's that angle measure, everybody, in radians? Pi over 2. Oop, that didn't come out very well. There we go. A little better. Hey, I'm going to just grab the calculator for this. And let's check it out. Ready? Inverse cosine of 0. And does that number look familiar? Yeah, it should. That's pi over 2. Also, I'm going to go ahead and bring my screen up one more time. Let's see. There we go. What do we say? Inverse cosine of pi over 2, or inverse cosine of 0, excuse me, is pi over 2. There we go. 0, pi over 2. All right, a lot to deal with, huh? Let's see if I need to cover anything else just in that. I think this diagram works great when talking about inverse cosine. So draw pictures. I think it's helpful. Okay, last piece. So example 3. Use a calculator to evaluate the expression to 4 decimal places. And let's just answer these real quick. So I guess here's what I would say. Kind of summarize this piece. When we do the inverse sine or the inverse cosine, the calculator is programmed to give you one of an infinite number of angles that have that particular ratio. The angle is in the intervals that we defined. For sine, everybody, your answers, your angle intervals are from negative pi over 2, which again is about negative 1.57 ... And let me just do this, put an and there. So from negative pi over 2 to pi over 2, which again is about 1.57 ... Okay, so when you do inverse sine on the calculator, it will only give you numbers in between those, if it's defined at all. For cosine, of course, it's different. When you do inverse cosine on the calculator, it's going to be somewhere in between 0 and, let's see if this works. Come on. So 0 and pi. And remember, pi, of course, is around 3.14, et cetera there. So watch what happens when you do the inverse of all these. Should work out nicely. So let's see, I have some of these on the paper. I'd actually encourage you to pause the video for a moment. And I know it's been a lengthy lesson here, but finish with a flourish if you would. Take the calculator. All you have to do is inverse sine of these numbers, inverse cosine of those numbers, and to 4 decimal places if you would on your calculator. So pause the video, come on back. I have mine written down here, and we'll see how you did. All right, so here's what I have. When you do the inverse sine of 1/4, you get a number in between negative pi over 2 and pi over 2. There it is. When you do the inverse sine of negative 0.65, I'm just going to go vertically if that's okay with you, I get about this right here. And when I do the inverse sine of 0.427, I get this right here. Come on, 4412. Okay, so inverse sine will always give you a number somewhere in between about negative 1.57 and 1.57. Okay, when I did inverse cosine, everybody, remember the interval's a little different. So for this one, I got about 1.2310. Inverse cosine of 0.9, I got about 0.4510. And last but not least, everybody, this one, if you remember, and if you did it, came out as undefined. Can I ever have a cosine ratio above 1? Absolutely not. If the cosine ratio is in our interval between negative 1 and 1, the answers will always be between 0 and pi. Obviously, if my cosine ratio is above 1 or below negative 1, that's not defined. All right, well, we will stop right there. There is a lot to process, of course. There's a day 2 to put a few more things together and a day 3 to review some things. So give it some time. Please ask questions with this. Do the independent work, of course, and help each other out. And let me know how I can be of assistance. Thanks for listening, of course.